Hello and welcome to this course. Today is the day first of second week. In the last week, we looked at the symmetry elements of any given structure, and we also looked at the basic mathematical framework called group theory. We learned how to form a group, what are the requirements, and we tried out a few simple problems, and also we learned how to find out the symmetry elements of any given molecule. So the main idea of this week's lecture, and to some extent for the following week also, is to classify the molecules and their symmetry elements in terms of a particular mathematical framework called group. So what we would learn in this particular week is how to find a point group, so-called symmetry point group, for any given molecular structure, or in that way any given structure, so that we can classify different molecules under different type of this groups, and utilize that to find out different other properties. So let's get started. First we will look at today how to find out the symmetry operations from the symmetry element for any given molecule. Okay. So our aim is to find out all the symmetry operations that is generated by a given symmetry element. So we have 5 different symmetry elements that we found out last week. Identity, we have proper axis of symmetry, we have center of inversion, we have improper axis of symmetry, and we have plane of symmetry or reflection symmetry. So let's do one by one. Okay. So the identity operation E, if I operate E on any molecule, it will give me back the same molecular structure, and if I operate it once more, it's not going to make any difference. So you operate E on any molecule n number of time, infinite number of time, every time it's going to give you back its original structure. So one identity element E will generate only one symmetry operation, that is also E. So if these are my elements and these are my symmetry operations, okay. So these are symmetry elements and this part will be symmetry operations. So E element will generate only one symmetry operation, that is identity operation. Now next will be proper axis of rotation. Okay. So any given proper axis of rotation is denoted as Cn. N is the order of rotation. Now we mentioned about it when I showed you the example of methane molecule. Okay. That once I find out which one is my C3 axis, in that particular case Cn was C3. So once I locate that principal axis of symmetry, then for every 360 by n degree rotation, I get an indistinguishable Chuck structure. Okay. So that means I can keep on operating Cn till the point I get back my original structure. So, for example, in case of methane, I had the C3 axis, and you start rotating, 120 degree, 120 degree, 120 degree, and ultimately you will end up getting the original structure. So, you keep rotating the molecule about Cn. So, the first rotation will give you Cn1, second rotation will give you Cn2, and so on. And when you reach Cn, that means you operate a 360 by n degree rotation. For n a time, you will get back the original structure. So, for any given Cn, you can generate n number of operation. Now, out of this n number of rotational symmetry operation, this nth rotation will actually give you back the original structure. So, operating Cn on any molecule will mean that you are as if operating identity operation. So, Cn is nothing but identity. So, that already we have one. So, in that sense, what we mean is for a Cn symmetry element, I can generate Cn n minus 1. So, the total number is Cn operations. You can generate n minus 1 operations, right, starting from Cn1, which is normally written as Cn, to Cn n minus 1. You do not have to go to Cn because it gives you identity operation. All right. So, next let us worry about sigma plane. So, sigma plane is a symmetry element in a given molecule. Sigma is what it does. It reflects any molecular structure, okay, across that plane. So, if you operate sigma, you get an indistinguishable structure. If you again operate sigma on that, what you get? You get the original structure black. It is as good as like you are standing in front of a mirror. Okay, your left and right hand will be interchanged. Now, if you have another mirror on your back, the reflection of the first mirror will go there, and you will see your right hand is on the right side only. Okay, so you get original structure back. So, if you operate sigma twice, it acts just like an identity operation. So, in that sense, sigma will generate only one operation, and that is also called sigma. Okay. Now, what about center of inversion I? So, center of inversion I, when we operate the symmetry, we call it it's an inversion symmetry operation. So, that is also written by I. So, all the symmetry elements and symmetry operations, they have the same symbols. Okay. In case of operations, you keep on doing the operation as many times as you can until unless you reach identity. So, for inversion operation, what you have, you just invert the any particular given point in a body, right. So, that means if you have one molecule which has a center of inversion, which is actually called as centrosymmetric molecule, because this is center of symmetry also. So, if you have a molecule which is centrosymmetric, meaning having I, then any given point at in any particular coordinate will be exactly inverted. So, if you have a coordinate x, y and z, then passing through this center of inversion, you will get minus x, minus y, minus z. Now, you see, after doing inversion operation, you come from x, y, z to minus x, minus y, minus z. If you again operate I on this one, what will happen? This will now go here. So, first I, it takes it here, second I takes it back into the original place. So, that means if you apply I twice, it is as good as an identity operation. So I also, we can see, generate only one operation, that is just one inversion. Now we are left with the last one, that is improper axis of symmetry and the symmetry operations generated by this symmetry elements. Now here the things are a little bit different. This number of operations that you can generate is very much dependent on whether it is n is even or n is odd. Now what we will do, we will we'll find out how many operations this Sn can generate when n is even. Okay? So Sn is nothing but a Cn followed by a reflection on a perpendicular plane that we call as sigma perpendicular. Okay. So now when n is even, let's take a particular example. Okay. So I will take S4, that is equals to C4, that means a rotation by 90 degree followed by sigma. I am omitting, I am not using this perpendicular anymore because this is perpendicular plane. So for simplicity, I am not writing this perpendicular anymore. I am just writing sigma. But remember, this is a perpendicular plane, perpendicular to this C4. Okay. So now I operate S4 once, that is this. If I want to operate S4 second time, then it is S4 2, which is nothing but C4 sigma 2. All right. So which I can write simply here C4 2 sigma 2. Now we have already seen that sigma, if it is applied twice, it generates identity, right? So identity means I don't have to write anything here because identity operation will end up giving the same structure, the identical structure. Okay. So this means equals to C4 2. Now think about this. C4, when it is operated twice, that means 90 plus 90, 180 degree. I can actually have axis which is C2 here. C2 will transfer the molecule, rotate the molecule by 180 degree. So C42 is nothing but C2. So I have generated this one. This is a symmetry operation by itself, and this one S42 generates another operation C2. Similarly, if I go to S43, without doing all these things, I can now write. I can jump the steps. So it will be C43 and sigma 3 means sigma followed by another sigma. So 2 sigma will give you E. So you have E followed by sigma means sigma. So I have this. This is also a unique operation, right? Now if I can just rub this part. Then I can go to S4 4. That means C4 4. C4 4 means what? CNN, meaning identity. So that is not going to give me anything, and sigma to the power 4 is also identity. So S4 4 is identity. All right. Now we have said that for any given symmetry elements, we start generating the symmetry operations until and unless we reach the identity operations, and we have reached there. So here this S4 generates 4 operations, out of which one is identity and 3 others are symmetry operations by themselves. So here Sn will generate Sn 1 to Sn n minus 1 operations. Also there is E for Sn n. Okay, when this is even, this is for even. Okay, all right. So essentially they are generating n number of operation, and out of this n, one is identity, and then rest n minus 1 are other operations. Okay, so this is pretty much like the Cn. Cn also does a similar thing. Now let's see what happens in case of when n is odd. Okay, so let's take a simple case of S3. 3 is an odd number. So S3 means I have a C3 followed by a sigma. All right. So this is S3 means S3 1, and I operate it twice. I get C3 square and sigma square means identity. So this is C3 square. So this C3 square we have also generated for proper axis of symmetry if Cn is C3. Okay. So S32 is nothing but C3 square. Then I go for S3 3. This is C3 3 meaning identity. Okay, and sigma 3 means sigma. So S3 3 generates a sigma. Okay, so this is true for any odd order of improper axis of symmetry. When I operate it in a way like when Sn n, I generate a sigma when n is odd. This is true irrespective of any order. If I take S5, then S5 5 is sigma. It's easy to find out because S5 5 means C5 5 sigma 5. Sigma 5 will generate sigma and C5 5 will generate E. So you end up with only sigma. All right, move on to S3 4 because we have not reached identity yet. So we will see what is it. So C3 4 means C3 3, if I expand this one, C3 4 sigma 4, sigma 4 is identity. So you have essentially sigma 3 3 and sigma 3, which is, this is identity. So we are left with only C3. So I can write here that S3 4 is nothing but sigma is C3. All right. S3 5 is C3 5 meaning C3 3 and C3 2. C3 3 is E, so I am left with C3 2. And sigma 5 odd number, so it will end up giving me sigma. This is also a new operation that is not present here. Okay. And if I go to S3 6, I have C3 6 means C3 3 followed by C3 3. So two identities I am getting, and sigma 6 even number, it will generate only E. So S3 6 is E. So what I get here, for an odd number of n, Sn will generate total 2n number of operations. Okay. Out of this 2n, one is identity as ever. So here I get Sn1 to Sn 2n minus 1. These are independent symmetry operations, and the 2nth number is nothing but identity. Now also you see here there are important thing that I already mentioned, that Sn equals to sigma for n equals to odd. All right, and in this particular case you see this S for when n is odd, Sn will definitely have an Cn. Okay. So this is an important consequence, and if you remember what I did for Sn when n is even, that Sn when n is even, Sn will make sure that you have an Cn by 2. Okay. So if you go back to the previous case of Sn when n is even, you can verify that one. So this is the case of Sn when n is odd. So Sn even will generate n number of operations, out of which n minus 1 number of are independent and nth one is the identity, whereas Sn when n is odd, you can generate 2n number of operation where one is identity. Okay. So fine, we will need these things very soon. So we found out how to get the symmetry operations or how to generate the symmetry operations from a given symmetry element, okay, for all identity, proper axis of symmetry, reflection symmetry, inversion symmetry and improper axis of symmetry. All right. Now next thing we should learn is how to combine the symmetry operation, or in other words, if I operate like I generated different symmetry operations by successively applying the symmetry operations on a particular molecule, Cn, one more Cn, one more Cn in that way, or Sn, one more Sn in that way. Now what I did here is, so we are going to learn about combination of symmetry operations. Okay. So in the last case what we did, we operated Cn and then again we operated Cn. Now what happened if I operate say Cn followed by I? What will happen if I have sigma? We have seen that if I operate same sigma plane twice, then I get back the identity. Now if I have a case where I have two different sigma, okay, for example, I take this molecule water, right? So here I have two different plane, one is containing this molecule as a whole, all the atoms. So this plane of this board will constitute one sigma. So let's call this one as sigma, and then another one which will be perpendicular to this plane, right, cutting this molecule into halves. Let's call this as sigma b prime. Now my question is, what will happen if I operate sigma b and then sigma b prime? What is the result? I should know that. Okay. So essentially what I am asking is, what will be the result of a binary combination of two different symmetry operations? I have seen already what happens in case of the combination of the same symmetry operations with itself. Now we are going to see what happens in case of two different symmetry operations. So let's take this example. This is the simplest example. So let's start with this particular question itself, right? So now in order to solve this, what we will do, we will first mark these hydrogens by 1 and 2. Okay? So this is 1 and this is 2. So I am going to do is, what I am going to do is, I am going to apply this one on this molecular structure. Okay? Correct? So what I will do, I will first operate sigma b prime on this, and then whatever the result that I get, that is the resultant structure, I will operate sigma b on that. Let's do that. So when I operate sigma b prime, that is this plane, okay, which is cutting half, then what will happen? 1 will come to this place, 2 will go here, nothing will happen to O. So I get a structure, right, like this. This is 1 and 2. Now if I operate sigma v on that, what is going to happen? So sigma v is in this plane. So sigma v is not going to do anything to this molecule, so that will remain same. So ultimately operating sigma v and sigma v prime on this molecular structure will give me this one. Now can you tell me could I get the same structure from this starting molecular structure by operating any other symmetry operation? A closed loop will tell you the answer is yes. What is that? I have a rotational axis of symmetry, right, along this direction, which is a C2, right? If I rotate this one, then I get equivalent or indistinguishable structure. So now, if I operate C2 on this structure, what will happen? This will just rotate it 180 degree. So one will go over to the place of 2 and 2 will come here, which is nothing but this. So I can bring this structure to this by simply operating a C2, and I can create the same effect by combining these two. Okay? So this is an example of how to combine this. So what you should do is you take any molecule, find out the symmetry elements, and then you find out the symmetry operations, generate all the symmetry operations. So you find the exhaustive list of the symmetry operations that can be generated for a particular given molecular structure, and then you start combining any two symmetry operations. How will you do that? Just like this. You take the molecular structure, operate one, then whatever the resultant, operate the other one on that, and you get your results. You can combine like 5, one after another, and you can end up getting that the desired result. Fine. So we have learned how to combine this symmetry operations. Now we are pretty much ready to check if we can use this symmetry operations that one molecular structure can generate, whether they can form something like a group. Okay. If it is capable of forming a group, that is the symmetry operations of a given molecular structures can form a group, that will be wonderful, because we can utilize all the properties of a group, okay, to define the symmetry of the molecules. When I say the define the symmetry of the molecules means we can classify several molecule into a particular group. Then we can utilize the characters of those group. Okay, note this particular word character. Here I just meant a character, like a characteristic thing, but it has another meaning also, which will be clear in a week or so. So we have to check whether this symmetry operations can form a group or not, and that will really help us in finding out how the molecular symmetries dictate the observation of several properties, chemical or physical properties. So we'll stop here today, and in the following class we will look into this possibility of formation of a group using this symmetry operations as the element of the group. Thank you very much.